I'm the director of the CAPE. This is the CAPE Acorn Fund presentations, including the presentations for the Acorn 2B Projects Award and the CAPA Projects Award, which is for Postgraduate Research Award. And we have 6 presentations today, and it's scheduled between 10 o'clock and 11:30. We have the CAPE Steering Committee members and also the staff of the university and the students attending it. So this is a popularity of being virtual. And I think there will be people join in and out from time to time, but I think we make it flexible. The first presentation will be given by Georgios Batzolis, and he is one of the 2B projects winners on the 4th year project, which he just finished. And the title of his presentation, slightly modified from his 2B project. The title is In Super Resolution Using Deep Learning. So Giorgio, now it's your turn to share the screen and start. You can introduce yourself.
Of course. Okay, I will start now. Just a moment. Okay. I hope it is shared now. Is it okay?
Sure.
Can you see my screen?
Yep, we can see it.
Okay, then I will start now. Okay.
I can see it, yeah.
Okay, perfectly. My name is Georgios Batzolis, and my project is on multimodal image enhancement using deep learning. My industrial supervisor was Jose Costa Pereira, who works in Huawei R&D, and my university supervisor was Professor Tim Wilkinson. And I want to thank them both for the guidance and support that I received from them. The aim of my project was to train a neural network to learn how to enhance a low-quality image in different ways, as you can see in this slide. The mathematical formulation is the following. Given a set of low-quality and high-quality images, where most of them are unpaired, we want to model the distribution P of y given x, where x is the low-quality image and y is the high-quality version of that low-quality image x. In practice, this task is a specific instance of multimodal image-to-image translation. For example, below you can see the image translation task of a face of a man to the face of a woman and vice versa, which is a different image-to-image translation task. These multimodal image-to-image translation tasks are usually performed using image-to-image translation deep learning frameworks. My initial research led me to 3 of them, DRIT, MUnit, and augmented cyclogram. I conducted experiments on all of them, and I realized that augmented cyclogram is the most suitable one for the task of image enhancement. Recently, there was a new framework which was published, which is called Stargan, the second version of Stargan, and it is currently the state of the art in image-to-image translation. However, I didn't have time to conduct experiments on that one because it was released very lately. I'm going to describe the augmented cyclogram framework now that I used. The theoretical goal, as I said before, is to model the distribution P of B given A. How this is done in practice is the following. In practice, we're trying to learn a mapping, GAB, I call it GAB, from the augmented space A times ZB to space B, where A is the space of low-quality images, B is the space of high-quality images, and ZB is a latent space which describes exclusive domain B characteristics. During inference time, what we do is that we receive a low-quality image A, and then we sample from the latent space ZB, and we pass both the low-quality image A and the ZB sample from the ZB latent space through the trained generator GAB, and we receive an enhanced version of the low-quality image A, which is image B. By sampling different latent vectors ZB from the ZB latent space, we're essentially getting slightly different enhanced versions of the low-quality image A. Now I'm going to go through the training framework. The training framework is very, very complex. It consists of 80 neural networks, 2 generators, 2 encoders, and 4 discriminators. And the training takes place in 2 cycles, which are based on adversarial learning and cycle consistency. On the left, you can see the cycle starting from the augmented domain A times at B. I will not go through the specifics though during the presentation. Training on the original model. I initially re-implemented the model using TensorFlow 2.0, and I trained the model on a well-known dataset which is called DPED, and it's a very well-known dataset in the image enhancement community. My training results puzzled me because as you can see on the left figure, you can see that there are a lot of color shifting artifacts. However, I realized that the model had the opportunity to perform well if I get to the root of the problem that creates the artifacts and resolve them. My long experimental research on the causes of the artifacts led me to the conditional instance normalization layer. This layer was the cause of the artifacts, and its use was to essentially incorporate the latent vector into the main generator. This layer was very important because it was the layer that introduced the stochasticity in the output and essentially the differently enhanced images of the same image. The authors of the paper essentially had taken that idea from a well-known paper which is called StyleGAN. And this model, the StyleGAN model, was essentially the state of the art in unconditional image generation a year ago. However, the authors of StyleGAN paper released a follow-up paper this year and explained that some of the artifacts that were created in their initial state-of-the-art approach were created by that specific layer, the conditional instance normalization layer. And as a solution to that, they proposed a new layer which is called weight demodulation. So I just followed their ideas because I could see similar problems in my implementation, and I replaced CIN by weight demodulation, and I managed to resolve the artifacts. After getting a decent performance without those pronounced artifacts, I realized that I was done, but then I realized that that was not the case because of the quality diversity trade-off. What is quality diversity trade-off? First of all, I want to explain that quality is measured in terms of the perceptual quality of the enhanced images and also with respect to the similarity to the ground truth, the similarity of the enhanced image with the ground truth low quality image. Moreover, we have the diversity, which measures how different the multiple enhanced versions of the initial low quality image are. There is a natural trade-off between quality and diversity. And my model, or the augmented cyclic framework that I used, provided no control over the trade-off. So at the end, how good in terms of quality or diverse my output enhanced images were could not be controlled by me and was essentially predetermined by the structure of the model in an unknown and uncontrollable way. I realized that it was very important to find a way to indirectly control the trade-off because in different applications, we might want more diversity or more quality. My research led me to different regularization schemes to control the trade-off. First of all, I explored the mode-shaking regularization scheme. This scheme, and essentially what it does is that it tries to increase the diversity at the output, but it does so at a very significant price on quality. And I realized that this is not a complete solution because what I want essentially is to be able to increase the diversity in the output with the least compromise on quality. And as a solution to that, I found the perceptual path length regularization scheme. This scheme motivates smooth mappings from the latent space to the image space, and as a result, it has the tendency to increase quality with a very small compromise on diversity. So as these two regularization schemes seem to have an opposite nature, I realized that if I use a mixed regularization protocol, which uses both schemes simultaneously, I would be able to increase the diversity with the least possible compromise on quality. and the relative frequency of the calling of the two different regularization schemes would be able to set the diversity with the least possible compromise on quality. Now I'm going to describe the mixed regularization scheme that I used. There were a lot of ways to conduct this regularization protocol, and I realized the best one in my case, after a lot of experimental research, was that I would separate the training into two stages. During stage one, I would use both the regularization schemes, and the relative frequency of the use of them would set the diversity. During the first stage, the PPL smoothened the mappings and resolved the resulting artifacts from the mode-changing regularization scheme. However, at the end of the training, there were always some artifacts which would still remain. So for this reason, I introduced the second stage where I used only the PPL scheme. And the PPL scheme managed to resolve the rare artifacts, which were found at the end of the first stage. And at the same time, I realized that the PPL doesn't really affect the average diversity. In fact, the average diversity was slightly reduced. Now I'm going to show you some results. Here you're going to see the results after the first stage of the training. On the left, you can see the low quality image. In the middle, there is a GIF which shows random samples of the enhanced images which correspond to the left low quality image. And on the right, you see the ground truth high quality image, which is taken from a DSLR camera. As you can see, there are pronounced color shifting artifacts. Now, during the second stage of the training, where PPL was only active and managed to smooth the mappings and essentially push those artifacts towards the very unlikely regions of the learning space, you can see that the results no longer suffer from the pronounced color shifting artifacts, while the diversity is essentially about the same as before. At the end, I realized that the PPL regularization scheme seems to motivate the optimal compromise between quality and diversity. So what I did was that I trained the model from beginning to the end using only PPL active, and I completely disabled the MS regularization scheme. And here are some results that I got. Conclusions. I achieved multimodal image enhancement by making crucial modifications to the augmented cycling framework, and I also introduced the mixed regularization protocol in order to control the diversity quality trade-off. I believe a lot of the changes that I made and a lot of the contributions that I introduced could be beneficial for a range of multimodal image-to-image translation tasks, which I aim to explore in a later general study. Finally, I think this work could be used for the creation of a tool that would be able to explore how the human brain perceives a superior image quality. Thank you for your attention.
Thank you very much, Georgios.
Okay, of course.
Now it's open to questions.
Of course.
I've got a question.
Yeah, sure.
So the couple of the results that you had there, so particularly like the cars with the license plates, you could sort of make out some of the, it looks like you could make out some of the letters slightly more clearly and things like that. Was that because, did you like do any checks to make sure that writing and text and things were actually accurate, or was it just sort of the resolution makes it look like there are more discernible letters there, but it might not be letters that we ourselves might be able to recognize?
I'm sorry, I haven't really understood the question.
So I was wondering. So some of the license plates on the cars, you can make out some of the letters more clearly. Did you specifically look at whether it could actually affect text to make it more legible, or was that sort of not an area you really looked into?
Basically, the task of image enhancement is, of course, to make things more legible or more tactile to the human eye. But for example, if you want to make it that specific, you would need a data set that would contain, for example, a lot of plates of cars, so that you can get an increased performance in that specific task. But since my dataset contained probably the plates of cards would be very scarce in the dataset, so I wouldn't expect it to make it that much clearer. But in general, the model should be able to enhance any image that it would receive. So I haven't really looked specifically at the plates, but in general, it seemed to produce a very good performance in general settings.
So is that like an example of the quality versus diversity sort of trade-off?
I'm sorry?
So is that like an example of the quality versus diversity trade-off you were speaking about?
Yeah, it could be. For example, if you want to get a lot of different versions of the enhanced image, which are semantically different, at some point you're going to lose quality, and it's very likely you're going to lose quality because quality is measured in terms of two things: how similar my enhanced image is with a ground truth low quality image, with the initial low quality image, and how perceptually appealing it looks to the human eye. So if you're aiming to get a lot of diversity, then it is very likely that some of the enhanced images that you get, they're going to have a low quality. But this might be desirable in the cases that you want to see different versions of the enhanced image, so that somebody who looks at it could say, okay, this is what I want to look at. For example, if it is aimed at forensics. I don't know if this makes sense.
That's great, thank you.
Thank you very much. In the interest of time, we will move on. If you have questions, you can contact the Georgios directly. Thank you, Georgios. Thank you.
Thank you very much.
Thank you.
The next speaker is Oliver Jones. He's also part to be project award winner, and his title is Model Localization and Terrain Mapping for Tabletop Wargames. So something should be interesting, Ollie.
Great, thank you. Let me just bring up my screen share. I'm afraid my camera is notoriously broken, but hopefully you can. Can you all see my screen fine?
Yeah.
Yeah.
Great. Wonderful. So yes, so my project on model localization and terrain mapping for tabletop war games. So for those of you that aren't familiar with the wonderful, wonderful game that is Warhammer, it is a strategy game played between two players, and you can see sort of an example board on the right. Each player has an army of sort of a couple of inch size miniatures, and units interact with each other using a dice roll. So on the right, you've got sort of like a typical size game, but you know, these can scale up to sort of this size game. So this is actually a diorama, but you could in theory play a game on this board. I mean, for size of scale, that's my three friends at the back, up the stairs near the top of the board. And so when you've got sort of large boards like this, one of the problems that can occur is the problem of line of sight. So it's a crucial to sort of interactions within parts of the game, because what a model can see depends on what it can sort of attack and shoot. And particularly when you've got sort of dense boards like those that you saw earlier, a player getting their eyes down to that model's eye view can be very difficult without disturbing the miniatures on the board, which can cause sort of disagreements and things like that. So this project is based around sort of solving this problem by creating sort of a digital reconstruction of the board. So these are the sort of all the areas that I sort of covered throughout the project. But for today, I'm mainly going to focus on these areas just for the sake of sort of time. So first off is sort of the registration tasks. So I've created, so I was able to capture some 3D images using sort of an Intel RealSense camera. So it's sort of like a Kinect. So it natively produces these 3D images. So what you can see on the right is two misaligned point clouds. And so what we want to do is we want to take several views and combine them. So we've got one sort of 360-degree view and then start to analyze that. So this registration process is about aligning these clouds into a sort of more tighter alignment, as you can see here. And then you can do more detailed sort of like outlier removal and things like that. As you can see, there's sort of like several artifacts that get produced. So the main sort of engine behind this is the iterative closest point algorithm. And so this is an optimization. So you've got two cost functions at the bottom. So if you've got a target point cloud T and a misaligned point cloud S, you want to optimize these cost functions to find the transformation M that will take all the points in S and map it onto T. And so there's two main flavors of this iterative closest point. There's point to point, which is on the left, and point-to-plane, which is on the right. So point-to-point, as the name suggests, just merely minimizes distances between points that are believed to be the same point between the two clouds, whereas point-to-plane just ensures that points that are thought to be the same between two clouds are merely in the same plane as one another. So this makes use of the estimated normals of each point within the clouds. That's the end that you see there. And then this iterates and re-estimates the correspondences until you get a tighter and tighter alignment. But one of the problems with iterative closest point is that it's very sensitive to the initial alignment. And so you've got to be able to have a way to find this rough initial alignment to have any sort of chance of getting a good reconstruction at the end of it. So in the data sets that I used, I made use of a building and 4 miniatures on a board. And so since I knew that the building would always be present in each of the scenes and is clearly the largest object, it's very easy to identify, and then I find the corner of this building. So as you can see, you've sort of got the two planar walls. And so to find the initial alignment, in my case, I created sort of a ransack least squares sort of algorithm that fits two lines that are 90 degrees to one another to a set of points. So as you can see on the left, we've got 4 of the building views if you view from the top down. And you can see that it finds the edges of the building really quite well. And then taking multiple views, applying this algorithm and aligning all these sort of corner points together, you can get sort of the rough initial alignments that you see on the right, which I think you can agree is pretty good, close initial estimate, which works really well to then be tightened up using this iterative closest point that I just mentioned. And so then you can see you get a much more tighter view, and you can get a full 360-degree feel for what's going on. And so the overall process, so first of all, we segment to find the building. We apply this ransack fit that I've just described to get this initial alignment. And then we align all the views with one another using this iterative closest point. So now that we've got a more full picture of a tabletop board that we're looking at, we now want to be able to actually cut out areas and segment them to propose regions of interest for classification, as well as to identify the building initially. So the main segmentation algorithm I use is dbScan, or density-based spatial clustering of applications with noise, which is a little bit of a mouthful. But this is a really good clustering algorithm because, first of all, it can find any arbitrary shape cluster, and similarly, it can find any arbitrary an arbitrary number of clusters, which is good because we can have any number of models on the board, and they can be any sort of shape. Really, there's no sort of set shape that they can be. And so this algorithm works really simply. So it's got 2 parameters. First, you've got a distance r and a minimum number of points p. And so it first of all classifies all the points that you see in blue as the points that have at least p points within a distance r, and that's all the blue points that you see. Then all the yellow points are those that are within r of a blue point. So these form the edge of a cluster. And then finally, you've got the points which don't classify either of these as which you see in red, which is good because it means it can find outliers, as you saw in sort of the previous registration examples, because the cameras can produce sort of several different artifacts. And so how does this actually look like in process when you apply it? Well, when applied to the scene, as you can see for 4 different layouts, it can really easily identify distinct separate clusters. We do have the problem of in the top right and bottom left cases where there's models in the building where it classifies them all as a single cluster. But otherwise, what you see is a really, really high quality sort of segmentation. We do still get some artifacts as well. So again, as you can see in the top right example, you see that sort of red line at the edge of the table and things like this. But these can be very easily filtered out using simple height checks. So we know that our models are only going to be between certain height ranges. And similarly, using singular value decomposition, we can find linear regions. And we know that if it's got a singular value close to 0, it's not going to be a model because it's not a fully 3D object in the 3D space. Great, so wonderful. We've got our segmentation now that we can actually begin the classification process. And so to begin to actually classify the models in 3D, I needed a set of reference models to create. So initially on the left, I tried to create them just by cutting out the point clouds that I created and aligning them individually. But as you can see, these point clouds are very, very noisy. And I had trouble for creating them with the smaller miniatures, so I had to find a different way of doing this. But instead, I looked at photogrammetry options. So these are, as you can see, the results are much, much better. So this process works by taking a collection of RGB images, typically 100-ish images per model, evenly spaced around it so you can get that full 360-degree view. With these RGB images, you put it through structure from motion frameworks such as Alice Vision, and this can create a full 3D colored mesh, which, as you can see, these 3D models look really quite detailed. They've got excellent color to them and aren't very noisy. And crucially, they can, because you're using RGB images, they can work for large and small models, respectively. So what do we actually do with these reference models when we're actually classifying? Well, in fact, we actually go back to this iterative closest point algorithm that I spoke about before. So if we take those regions of interest and match it to each of these 4 reference models on the right, we know whichever one has the lowest cost function is the most likely to be matched. But we can take in a couple of extra pieces of information to sort of help our optimizations now that we have a fully aligned scene. So for instance, we know that all the models are going to be on the table, so they're all going to be oriented in a certain direction, which we can easily find by finding the plane of the table. That's a really simple operation. And because there's much less points, we need to use as much information as we can to match this. So taking our 2 cost functions, again, exactly the same as before that we see on the right, but instead constraining our transformation matrix to be a single rotation about the axis of the table, we can get a much quicker alignment process. So, and because again, we've got a much, much smaller number of points compared to the full scene, we can create some least squares solutions, which can be optimized very, very quickly for the classification process. So then matching these against and taking whichever one has the smallest cost function, we classify it as that model respectively. And so the bonuses of this, of doing it like this, is it also gives us the orientation of the model within the scene. And so you can see the classification using both the point-to-plane and point-to-point classification. And so as you can see, the point-to-plane is actually much more consistent. So we get about 80% accuracy here. Obviously, this is a small sample size. But whereas the point-to-point, it generally skews to one of the big models or one of the small models, respectively. And even in that case, as you can see at the bottom, the orientations are out. So the point-to-plane was the one that was focused on for the classification process. And in fact, then that allows us to fully reconstruct our scenes really quite accurately. So I think you'll agree, it's the comparison of the actual image of the scene on the right and the reconstruction on the left are really quite close. Excuse the black splotchiness. This was a bug in my visualization software where it didn't render the textures properly, but you can still make out the shapes, which is the important part. So now we can finally start looking at the problem of line of sight. And so visually, obviously, digitally, we can see what's going on here quite well, but we want to be able to automate this process in a computer just to tell us, can it see or can it not? So this is where I went back to an algorithm from sort of the mid-80s, which is raycasting. It was all used in Wolfenstein 3D, if any of you are aware of that game. And the process works by projecting a series of rays out from an optical center and rendering the objects in the 3D space based on what it can hit. And so this is sort of visualized in the bottom figure, as you can see here, where the black lines are sort of obstacles and bits of it are obscured from points that are in front. And so this is great because obviously it mimics how we would naturally perceive objects ourselves, and then it means it can deal with arbitrarily complex shapes again, deal with any sorts of holes and things like that. So I applied this in sort of a planar manner, as you can see on the top, a very sort of rough example. on one of the reference models, and you can see how from the front you can see the full model, but when you turn to the side you can see how it doesn't render parts of the leg and things like that, which are obscured from the hands that are in front of it. And so these are sort of preliminary results as I was getting towards the end of the project, but you can see how this could then be applied to sort of the whole scenes to determine which objects can be viewed based on whether they're even rendered in the first place. So in conclusion, what's been presented in this project is a number of things. So an original initial alignment method that uses least squares optimizations to find sets of corners and points. And then from these combined and registered scenes, taking those regions of interest and applying a much more efficient, constrained ICP to classify the model and create visually accurate digital reconstructions of the board space. The digital reconstruction can then be analyzed and used as an adaptation of raycasting to extend it to continuous lines through 3D space. So in terms of further work, ideally I would like to sort of enhance my classification to be more probabilistic. This obviously has the benefit of being able to deal with miniatures that are the same in terms of rules within the games, but might have different poses depending on how someone has sort of constructed and painted the models. Similarly, to make it more accessible to most players, I would like to move towards RGB image processing. So that's using techniques such as Apple's Measure app, which can find sort of objects in the 3D space and deal with that. And in fact, RGB images are much easier to do sort of convolutional neural network classification and things like that. And then finally, a lot of the work that I've been doing is offline. So I've been doing it largely in sort of Python and similarly related high-level languages. I'd like to sort of look at lower-level implementations, which would obviously give you much more benefit of speed and allow you to do these processes much more online. Great, thank you very much. Is there any questions?
Thank you very much, Oliver. Is there any quick questions? No?
No.
Okay. If you have questions, please follow up with Oliver.
Great, thank you very much.
Thank you very much, Oliver. We have had 2 wonderful talks on the Part 2B projects. Now we move on the CAPA projects, which are the studies of postgraduates. The first talk is given by Dean Kos, and his title is Integrated Adaptive Exposure Control for Image Cameras. Dean.
Hey. Yeah, hello everyone. Let me just share my screen. Share. Okay, can you all see my screen okay? Should pop up in a second.
Yes.
Yes, we can see.
Should I get rid of this? Somewhere else. Right. Okay, so good morning, everyone. My name is Dejan, and I'll be talking to you about the project I've been working on for the CAPE Award, which is about this integrated adaptive exposure control for imaging cameras. Let me just put the laser pointer here. There we go. So where does this idea come from? So as an amateur photographer myself, I often come across the problem that many imaging cameras have, which is that of imaging scenes which have high contrast. So a situation where you have some very bright light in some regions of the scene and some dark objects in some other regions of the scene. So this is a typical example that you may come across. So this is an image that was taken in the Maxwell Center here in West Cambridge. And what you see is that cameras can really struggle in high contrast lighting situations. So what you have on the left here is a situation where I try to, which is just taken a photo taken with my mobile phone. I've been trying to get a decent exposure of the foreground, so the objects that are inside the building, so these little chairs and tables and everything. And what you can see immediately is that everything that's bright, so the background which is very bright because obviously it's an outdoors situation, it gets completely blown. So you completely lose all the detail that is in the background of the scene. And you have pretty much the opposite situation if you touch your, so when you're taking the photo, you you tell the exposure algorithm to focus on the background. So you can now expose quite nicely the building on the back. You see the features, you see the details, but then you lose a lot of detail in the foreground, so the objects that you're trying to photograph. So this is a very common problem in photography, and there's quite a few ways around it. There's different ways in which you can do HDR imaging. There's filters that you can put in front of your camera, but at the very end of it, there's always some kind of artifact going on. So either it's the processing artifact when you try to make the HDR image, or in the first place, if you try to get it right in camera, then you have to use hardware kind of physical filters that would modulate the light, and these are always very difficult to apply locally. So the concept kind of that I wanted to test with this CAPE project is shown in this slide. So essentially, the idea is that you have your imaging sensor, which is what you find inside your camera, mobile phone or whatever. And then the idea was to put in front of it a liquid crystal panel. So this would be a pixelated panel that is typically found in displays, and there's millions of applications of liquid crystal panels. And so the idea is that if you can take a liquid crystal panel and place it right in front of the imaging sensor, you could take a high brightness, kind of high contrast scene and modulate the amount of light that hits the sensor on a pixel by pixel basis. So you would be able to get an improved exposure by controlling, by setting the right pixels to kind of different levels of dark, and you will be able to get from a high brightness, high contrast scene to an optimum exposure. So how did I go about doing this? So as you can see, there's two main components, let's say, to this project. One is the imaging part, which is the camera and possibly the lenses, and the other is the light modulation. So for the imaging, as a very first initial test, I just took a Raspberry Pi camera, which is quite an obvious choice because it's widely supported. There's lots of documentation on it. So that's what it looks like. The sensor of this camera is a few millimeters across, so the diagonal is about 4.5 millimeters. But the more challenging part, I would say, about the project was really about the light modulation. So actually finding a liquid crystal panel that would suit this application. So these liquid crystal panels, they come in all sorts of shapes and sizes. So you have the very basic alphanumeric ones. You have some which are kind of OEM kind of designed for small interactive displays. And the main problem is that they're all integrated into displays. And when you use a liquid crystal panel integrate for a display application, there's a whole set of layers that you want to put in front and behind of the actual liquid crystal panel. So you have the polarizers, which obviously are required for it to work, but there's a whole range of other layers that are used to optimize how the light is distributed across the panel. There's a backlight always on the back. So eventually so this was quite a long part of the project, actually finding a panel that would work. So ideally you would want a high pixel density on the panel that would sort of match the resolution of the camera. And this immediately turned out to be pretty much impossible because the resolution of the camera is several megapixels, whereas these displays, to find something that's cheap as well, it's really difficult to get a small, high pixel density and cheap display. So eventually I found this display here, which is a few centimeters in diagonal, maybe 5 or 6 centimeters diagonal. It was pretty easy to take apart, and a big part of the project was actually taking apart a whole bunch of different LCD displays and getting the liquid crystal panel out of it. So what does the initial kind of test setup look like? So this is what it looks like. So all the connections to monitors and input devices are not shown. So you've got the Raspberry Pi, you've got the camera, which is down here at the bottom. And this is the liquid crystal panel, which was obtained by taking apart a liquid crystal display. And this liquid crystal display is controlled by an Arduino, which is interfaced to the Raspberry Pi. So the Raspberry Pi essentially controls the camera. And what I do in a typical image acquisition procedure is that I take an image with the camera with the LCD turned completely off, so it's completely transparent. I acquire the image and I look at the regions which are very, very bright. And then I map those regions to that I see on the CCD of the camera, and I map those regions to the pixels of the liquid crystal display. And then I communicate with the Arduino through a serial communication to set those LCD pixels to dark. So essentially, that's kind of what was the initial concept of the project and what I proposed in the beginning. So what do you see when you do this? So these are some examples. The quality of the image is clearly not what you get with a phone camera or a proper camera. So these are also the whole thing is not particularly mobile because you always have to be connected to mouse and keyboard and a monitor to actually see what you're doing. So the top row is a series of images that I got with the LCD off, and then with the LCD on, kind of enhanced corrections going on. So this is just this pair of images is just the image of a ceiling. So you see that there's a ceiling, a room light on the ceiling, and what you see is that as obviously this whole region is detected as a bright region, so that's by the algorithm darkened by turning on all the pixels. And what you can see is that there is a big improvement in the amount of detail that you can actually see in this very bright region. So the rest of the exposure is the same. And all you can see here is that as we turn on all the dark pixels on the LCD, you pick up all the contours and edges of the room light and also the attachment to the ceiling. So big difference here in this bright region, which is actually able to reveal some more detail. So this is a situation, it's kind of more realistic. This is an image that I took from my apartment. And you see, again, it's an indoors to outdoors photography situation. And you see the bright regions, which are obviously outdoors, because it's in plain daylight. So what you see is that obviously there's some pixelation going on here, but the regions that were very bright have been darkened by the algorithm. And so you can pick up more detail in the floor here, which is completely blown in the picture above. The clouds, well, they're clouds, so there's not an awful lot more detail that you pick up from here. But you can see, for example, imagining to apply this to some contour detection situation, detecting correctly the edge of these buildings will be much more difficult if the image is blown. So this is kind of an improvement possibly for contour detection algorithm that may be taking place here. And finally, a similar situation, but with some ceiling lights with a slightly different kind of outdoor light intensity. Again, you can see that the algorithm applied to the parts of the ceiling can reveal quite a bit of detail that is hidden by very, very bright light. Now, there are obviously some drawbacks of this technology. One kind of concept, one is that you get an overall color cast on your images, and that's because the liquid crystal panel is not completely transparent. It has some, it's partially non-transparent, and it's not spectrally uniform in terms of the attenuation of the light. Obviously, you need a little bit more, about a factor 2 more exposure, longer exposure to compensate for the fact that you're using polarizers, which capture the total amount of light getting onto the imaging sensor. And because this liquid crystal panel that I was using was about 120 by 60 pixels, you get some quite strong pixelation artifacts where you use the LCD display. And finally, this particular liquid crystal display, I could set the contrast ratio, so how black the pixels are, but that was a single setting for the whole display. So I couldn't pixel by pixel modulate to make it kind of a grayscale change. It could only be on or off with a certain contrast that has to be set at the beginning. So after this, I started thinking of what could be a way to improve this. And ideally, you would like a high resolution display. So this has been quite a significant part of research that I've been doing kind of online and trying to find what is commercially available, what can people buy. And this is the closest thing that I've been able to find is an EPSO micro display, which is typically used in projectors like conference projectors or for presentations and so on. And so this is a transmissive micro display. So this is about 20 millimeters in diagonal. It's a full HD resolution. And this can be controlled as a normal display. So it's got 8-bit depth kind of gray levels. And this was paired with a board level camera, and these are very widely available with a range of sensor sizes. Now, the problem that I had with this was that the liquid crystal panel itself actually is not really very transparent. It's quite opaque. It's used for display applications. So I had a chat with the supplier, and it turns out that these micro displays have a micro lens array pattern on top. So each pixel has its own micro lens. And this, I think, is the reason why I was getting this opacity and also quite a few kind of iridescent and birefringent patterns. It's difficult to see here, obviously, but if you hold this in your hand, you see that you don't really get a clear image of what's behind it. So by talking to the supplier, there's a few factors that might come in here. One is probably the angle of the light that is used for this micro display. So you probably want the light, we want to include some kind of optics system that would make sure that the LCD, the light that goes through the LCD at pretty much normal incidence. And there's also some chromatic aberrations going on. So you possibly want something that's kind of a monochromatic beam going through the LCD. So I haven't really been able to obtain any good quality images with this method, although I would expect that this would improve the kind of pixelation artifacts that I was talking about before. So to sum up, I think that I've realized the initial aim of the whole project, which is to prove that liquid crystals can work as pixelated filters for imaging, and they can improve certain parts of the image acquisition process. We have to be aware of pixelation artifacts, and if we want to go for commercial panels that we can buy and use, then there's quite a big restriction of what we can currently go out there and buy. And it's likely that to make a proper liquid crystal panel work in this way, we need to include a full optical system where we have a set of lenses that would project the image of the scene that we're trying to capture and of the pattern that we put on the liquid crystal display to actually get a good quality image. That'll be all. Thank you.
Thank you very much. Any questions? It's a very nice result and showed here the improvement.
I have one question.
Yeah.
So if you compare, or did you compare with software-based approach or not?
I did not compare it, no. I kind of expected the software to be much better at this stage, to be honest. I mean, as a photographer, you know, there's a whole range of ways that you can go about bits of the images being too bright or too dark. Usually with bits of the images being too bright, there's not an awful lot you can do, because everything that goes above the saturation threshold of a camera, that's just is gone. You can't, the detail is completely lost, but you can, there's quite a lot of information in the dark pixels, so you can lift up the exposure of what to the eye look quite dark pixels and get out quite a lot of detail. So I think that in this version, there's no way that this technology can compete with kind of software-based HDR, but there is an advantage in the kind of high brightness situations, which I think is worth exploring further, at least. Yeah.
Okay.
So one question: do you need more time to do the exposure?
You do, yes. So all these tests that I've done have been, I've been using the cameras in kind of auto exposure mode, so I wasn't worrying about it too much. But yes, my guess would be definitely. Now it depends on what is the contrast that you're trying to image. So whenever you have a very bright object in the scene, you don't actually, particularly with a lot of sensors, you can get this blooming effect. So I think in some situations where you have a lot of light, and so the exposure speed is not a problem. So you don't want, so in very low light situations, I would avoid using this technique. But in high contrast situations that also have a lot of light in the first place, then I think this technique would be particularly useful.
Okay, thank you.
Okay, thank you very much. Thank you, Dean. Let's move on to the next one, which is, should be for Daoming Dong, but Andrew Kadis is stepping in. The title of the talk is Interfacing a High-Speed Ferroelectric Spatial Light Modulator.
Okay.
Andrew, thank you. Yeah.
Thank you. Can you all see my screen?
Yeah, not yet.
Not yet. Oh, I need to click the button. Is that working?
Now
Cool.
it's working.
Yes.
Cool. All right. So my talk today is on basically HoloBlade, which is the intention is to basically come up with an open platform for driving spatial light modulators for holographic display applications. Why is it not working? There we are. So firstly, just a quick recap on what exactly a spatial light modulator is. So spatial light modulators are a type of liquid crystal display which modulate the phase of light. But they can also modulate amplitude, but specifically for phase modulated holography, we're interested in devices which modulate the phase of light. And by being able to modulate the phase of light, you're able to introduce diffractive and interference effects, and that allows you to produce your holograms in your various applications. The thing is that contemporary devices are not very accessible. They're extremely expensive, for one. So just as a case in point, just before this talk, I went into Thor Labs and I had a look, what's the cheapest SLM you've got? And it's still $12,500 US. And that's like, it's not a completely fair comparison, but it does illustrate just exactly how pricey these things are. And then finally, because they are quite expensive and bespoke and exotic, a lot of the time the interfaces are very much unstandardized and proprietary. So, so you can't just take one SLM and switch it out for another one. You need to make sure that you're using a specific interface with specific driver boards and with specific interfacing software, and it very much frustrates research. So the motivation for this particular piece of work is to try and streamline all of that and put it into one particular standard to make research easier. So in order to actually do this, the key enabling technology is obviously the SLM. And I personally have access to a large number of very low cost ferroelectric SLMs. So I've basically been using them to, as the SLM for the initial implementation of HoloBlade. In the future, I foresee the spec being extended to support multiple SLMs, but you need to start somewhere. So particular SLM, it's a binary phase SLM. So you either get pi or zero phase. It's 1280 by 1280, so it's a reasonably high resolution, 5.6 micron pitch, and it can run up to 2.2 kilohertz, so it's particularly fast. So I'm going to go on and talk a bit more about the interface I've designed. One thing which I think technically is quite interesting and is worth highlighting is that a lot of the comms interface has been implemented in an FPGA as custom synthesized logic. And actually to do that, we actually used Python and a tool called MyHDL, which auto-synthesizes the logic. So I just wanted, and that's been very good to use. So I just want to put in a cheeky little plug for that here. Anyway, so talking about what we actually did, in order to build the full driver stack, starting from the bottom, you need to basically, well, you have your SLM, then your SLM needs to communicate with your custom driver electronics. So we built a custom board to communicate with the SLM. Above that, like on the actual custom board, we have our own FPGA where we've implemented all of our own higher level logic to marshal the data as it comes from the PC. And those comms are using USB 3. And USB 3 is then talking to the PC where we've put together a bunch of PC drivers, which then talk to a GUI application that we've put together to actually demonstrate the application. So just going through that again in a bit more detail, on the top right, you can see the custom electronics board that we've put together. The SLM itself is connected via that flexi ribbon cable. The majority of the work for the project actually ended up being in the FPGA logic. And you can see that in this block diagram here. So the communications between the PC and the custom driver electronics have been implemented using an FT601 chip, which is FTDI's USB 3 chip. So that gives us up to 5 gigabits per second of bandwidth, which is enough to achieve the timing requirements the throughput requirements that we actually want. That is then talking to a custom USB 3 controller interface that we've put together in the FPGA. The data goes from the controller interface across a dual clock FIFO. So one of the difficulties with this design is that there's a split clock domain. So most of the display update logic runs off the same clock as the SLM, whereas the data to come from the PC runs on the USB 3 clock. So actually marrying those together is quite difficult. And this dual clock technique handles that quite elegantly. And then as we go towards the SLM, we basically have the logic implementations of how to update the specific SLM controller. So that's all been implemented as a discrete update timing controller and as a discrete display data controller. And then there's a couple of other supporting little bits on the actual PCB itself. So there's some power circuitry and there's an external oscillator just to make sure that we get decent timing. In terms of what we've actually put together, you can see it together here in a bit more detail. So the custom PC, so we've put together a custom mechanical mount for the actual PCB itself. So we've done the custom electronics, we've done the custom mechanical mount, so that's been FDM 3D printed. That all slots in together relatively well. There's a bit of glue at the top. We need to do another revision. But it's quite easy to integrate into optical rigs. So this is a standard Thor Labs cage mount system. It just slides straight on. Underneath, we've actually put a standard optical rod mount. You can't really see it here, but it lets you just screw it onto a standard optical rod, and it means that you can just really, really lock the whole thing down, and it will auto-align to your optical system just based on its geometry, which is really good because these systems are incredibly sensitive and you just need to make sure that everything's as secure as possible. The SLM itself is a press fit interface into the front of the mechanical housing. So that just slots in there nice and tight and doesn't move anymore. And then there's a flexi ribbon cable between the SLM and the electronics board, as I talked about earlier. There were a lot of issues had with actually mechanical strain damaging the flexi. It's quite a trivial thing, but it ended up a lot of time got spent on actually making sure that the flexi itself was appropriately strain relieved. So this current design handles that really well. So this is not version 1. It took a couple of iterations to get it right. Right, now, moving on to results. So what you can see on the left is a custom optical system that has been built up around the SLM. And on the left, you can see clear diffraction effects. And so this is a standard 4F imaging system. You just basically shine the laser at the SLM and then imaging on a separate imaging arm. And you can see that there's a large zeroth order in the middle because the polarizers aren't set up properly. But beyond that, there's a whole bunch of diffractive effects moving across to the side. And that's demonstrating that the system is capable of producing holograms as a sort of initial proof of concept. The particular test pattern being shown on this image for this particular scene is a checkerboard test pattern. So you can see that on the bottom right. There's been because SLMs modulate phase rather than amplitude, you can't actually see what they're displaying normally. So there's just a piece of polarizer film on the top, just so you can actually discriminate that checkerboard pattern, which is a bit blurry, but you can see it. Anyway, so in terms of summarizing it and next steps and things we would like to do. So we've put together an initial implementation for HoloBlade. It's a full open source SLM driver stack. All the bits have been published online, so they're freely disseminated. One thing that would be very nice with this is for it to grow into sort of an ecosystem of holographic and SLM related support technologies. So because this entire driver stack is open and because people can build on it, it means that more advanced use cases such as on-the-fly data compression between the PC and the SLM, that they can potentially be done because they can tap into the existing driver stack, which is already there. So things that would be very interesting would be data compression, variable refresh rates, dynamic bit widths, some of these more advanced display features that we are actually seeing with contemporary displays in TVs, things like HDR and gamma correction, stuff like that. Shifting those into holographic display technologies would be really interesting. And HoloBlades is, I feel, a really good framework to actually do that. In terms of stuff to be done in the near to medium future, the first one really is to use the system in anger as much as possible, and just to get it in as many systems as possible and actually refine it. Secondly, it's currently using a custom C++ interface driver that we've put together. What would be significantly more useful as a research tool is if that was to be extended to include a Python and a MATLAB interface, and then you'll be able to drive your SLM directly from MATLAB. So that would be incredibly useful. And then finally, in the future, we would like to expand it to support additional SLMs. That would be quite a lot of work, but would be the sort of thing that I think really demonstrates the value of the platform. So yeah, anyway, that's it for HoloBlade. Any questions?
Thank you very much. That's wonderful work. Any questions?
Yeah, I have a question.
Yeah.
I'm wondering about the SLM modules themselves. Is that something that's available that you can buy? Because I mean, the big advantage of having an open platform is that you can kind of assemble it the way it's a particular application. So I'm wondering about the different bits which make the whole system. How customizable, how available are these? And
that's a very good point. So the SLM itself is these aren't the sort of thing you can just make in your shed. You need access to appropriate fabrication facilities. So the SLM itself is based on a proprietary design of an old display tech controller. So we have access to tooling and potentially to order more of them. I think that this is a case of you need to start somewhere. So we have access to this particular SLM. It is proprietary. It's made by one particular manufacturer, but let's try and make everything as open as possible. And then let's get more SLMs being supported, and then we can get multiple manufacturers on board. I think maybe a good analogy, I appreciate this is not a perfect solution, but that's sort of, I think, the path that needs to be trodden. I think a good example here might be the Raspberry Pi. So the original couple of Raspberry Pis, famously, the MediaTek chip used on them was completely closed source. They had to use the binaries which were provided by MediaTek. You couldn't even access the data sheet. However, they managed to build an open education platform on top of that. And I think this is sort of an appropriate situation here.
Yeah, I mean, it's completely sensible. And
I mean, the answer is you're exactly right, but you need to start somewhere.
Yeah, of course.
Yeah.
Yep, that's a good point. Thank you very much. I think we have to move on, and thank you, Andrew.
Okay, thank you. Bye.
The next talk will be given Murat Kuscu, and his title is Micro Nanoscale Molecular Communication System with Graphene bioFET-based receiver towards the Internet of Nano Things.
Yes, exactly. Hello.
All right.
Can you see my screen right now? Yeah, that's cool. Hello all, thank you for your attendance and for giving me this opportunity to talk about my recent project, which has been supported by CAPE Acorn Postgraduate Research Award. Well, the main objective of this project is to build the first micro-nanoscale molecular communication testbeds based on graphene biosensors and microfluidics to enable the practical applications of Internet of Nanothings. So what's this Internet of Nanothings? Well, it's the artificial networks of nanoscale functional units like nanobiosensors, engineered bacteria, which are integrated with the Internet infrastructure. Now, these nanoscale entities, which are normally of limited functionality, can communicate to each other to perform a more complex task like distributed sensing within human body with molecular resolution. So in that regard, it is promising for groundbreaking nanotechnology applications, especially in the healthcare domain. So to enable those IoNT applications, we need to overcome several challenges. We need to devise new communication methods because the electromagnetic ones do not perform well at nanoscale. We need to devise new biocyber interfaces to connect those nano networks to the wider internet. And these techniques should be energy efficient and low complexity because these nano things can be of very simple architecture. So the most promising method, communication method to enable Internet of Nanothings is bio-inspired molecular communications, as it is inherently biocompatible, energy efficient, and robust in physiological conditions. In molecular communications, the information is encoded into the concentration or type of the molecules, and messages propagate through diffusion in a fluidic channel in the same way the living cells communicate. But the discrete nature of the information carriers, which are the molecules here, lead to different kinds of noise sources. And also the channel is highly nonlinear, time varying, and also has a substantial memory. So we need to deal with new set of challenges here. And also, we don't have any working prototype of an artificial micro nanoscale molecular communication system to date. So the channel models and the communication methods developed so far are all based on unrealistic assumptions which are not experimentally validated. So to overcome this challenge, we set out to devise a molecular communication receiver that can convert the incoming molecular messages to electrical signals. So we look for an electrical biosensing solution, and we found that field effect transistor-based biosensors, also known as bioFETs, meet all the criteria we expect from a receiver. But bioFETs are very similar to the conventional field effect transistors, with the only exception of a biorecognition layer that is capable of selectively binding target ligands, which are the information molecules. So binding of those ligands to the receptors results in the accumulation or depletion of charge carriers in the semiconductor channel, and this modulates the conductance, and the output current becomes a function of the ligand concentration. And we decided to use graphene as the sensing material because of its high biochemical sensitivity, flexibility, and two-dimensional structure. So at the Cambridge Graphene Center, we set up to devise a graphene bioFET-based molecular communication receiver. We first built a graphene field effect transistor by using CVD ground, single-layer graphene. We have 7 transistor channels in parallel in a single device to compensate for any defects during the fabrication. And we also insulated the contact areas just to prevent the parasitic currents when exposed to an electrolyte solution. And then we built a PDMS-based microfluidic molecular communication channel and integrated it with the fabricated GFETs. And then we performed the biofunctionalization of the receiver with probe DNAs, single-stranded probe DNAs that can hybridize with the target DNAs, which will carry the information. We use linker molecules here to attach those probe DNAs to the graphene surface through a non-covalent reaction. And we validated the functionalization at each step by observing the doping level of the graphene based on its transfer characteristics. For this, we monitor the shift in the charge neutrality point of graphene. So this is the experimental setup, which actually stands as the first micro-nanoscale molecular communication system. Here, the transmitter is a microfluidic flow controller, which modulates the injection rate of phosphate buffer solution and the information DNA molecules. So we first obtained this sensogram of the receiver to determine its sensitivity, and we found that it can detect DNA concentrations down to 50 nanomolar. We then tested its selectivity in the presence of interferer molecules, which are also DNA molecules, but with different base sequences. And we saw that our device, the receiver, is sufficiently selective as it doesn't respond to the non-complementary DNAs as much as it does for the complementary one. And to determine the time-varying characteristics of the receiver, we sent 1 micromolar target DNA concentration as a molecular signal of varying pulse length. And then we fit the results to a theoretical model that I previously developed. So they seem to be in good agreement, but the model's accuracy is lower during the dissociation phase. And then we perform communication experiments by encoding the information into the concentration of target DNAs based on on-off keying modulation scheme. We sent pseudo-random binary information with different bit intervals, and we saw that the inter-symbol interference is very high for small values of bit intervals, such that the molecules, the information molecules, accumulate at the receiver surface, so the receiver is not able to return to its baseline. So applying a constant threshold for demodulating the binary information is likely to fail here. Instead, we apply a difference-based detection method, which just simply compares the current values between consecutive transmissions. We still observe a couple of bit errors, but this can be easily improved by applying a better noise-canceling filter. But the data rates are very low here, as you see. I mean, we are talking about hundreds of seconds just to send one bit of information. So these initial experiments actually show that the slow reaction kinetics at the receiver surface is the main bottleneck here. So the next challenge should be to devise new detection and modulation techniques that can increase the data rate without bringing too much complexity. So lastly, I want to thank my PhD supervisor, Dr. Akan, and advisor, Dr. Lombardo, and my colleagues who greatly helped me in building this testbed. I also want to thank CAPE Steering Committee for this prestigious award, which financially supported this project. Thank you very much.
Thank you, Murat. It's an interesting project. Any questions? So I have a question, Murat.
Yes,
what is sort of the sensitivity your bioFET can reach to the number of the molecules you're communicating?
In terms of number of molecules, or well, it can detect concentrations down to 50 nanomolar. So limit of detection is 50 nanomolar. But it is worse than the results in the literature. I mean, there are other bioFETs actually reported on graphene that can detect concentrations down to attomolar concentration. So, well, this device was not optimized from sensing perspective. So, detecting some kind of molecules would be enough for us to comment on its molecular communication performance. So, we try to optimize it from communication perspective. In terms of sensing, it's a bad device. I mean, not very good.
Yeah. It's more of the communication you are trying to build out.
Exactly.
Yes. Yes.
Exactly.
Yeah. Any other questions? Okay. If not, let's thank Murat again for the wonderful talk, and let's move on to the last one, which is to be given by Angkur Shaikeea. I hope I got your name spelled right.
That's fine.
And the title of his talk is Architect Cellular Metamaterials Hold the Future of Surgical Meshes. So, Angkur, please.
Can you see my screen, please?
Yes.
Yes, we can see that.
Hi, everyone. Yeah, the title of my talk is Architected Cellular Metamaterials Hold the Future of Surgical Meshes. So thanks to CAPE for generously funding the project. I'm a third-year PhD candidate. I'm moving to my fourth year this October at the Department of Engineering. So let's begin. Surgical meshes are like textile clothes, which are used to support organs when they fail inside our body. Like, when you have hernia or vaginal prolapse, it requires surgical procedures and you need to place a cloth-like material to support. And it has been used for quite a long time, about 30 years. So, as you know, 30 years is a long history. So the meshes have developed over time. The present generation meshes are called third generation meshes, and they typically look like one of these. Either they're knitted or they are woven. So as I told you that they are textile-based meshes, and the mesh materials commonly used are polypropylene and polystyrene, which are biocompatible, and the major manufacturer in UK is Johnson & Johnson. So why am I doing this with architected materials? There are several drawbacks, and the drawbacks are quite serious. So from a mechanical engineering perspective, the major drawback that they have is this is the mesh that I'm holding in hand. It has different properties in different directions. That is, the properties are anisotropic. We call it anisotropic. And the problem is when you do surgical procedures, the surgeon needs to be very careful in placing the mesh, because if you place the high strength direction along a very low loading direction, then it's subjected to failure soon. So recurrences are very high. It's more than 30%. Second is these biocompatible materials like polypropylene, when you weave it like a cloth, either they can become very stiff or they can be very soft. So in soft tissues, when you place a very stiff thing, it creates a lot of discomforts. But there are complaints from patients. Third is porosity. You cannot control the porosity, the pore sizes. Once you weave it, that's it. You cannot change the porosity. And porosity is important because of infections, the bacterial growth. So these are the three major things which caught my attention, and I thought, why not try something different? The scale of the problem, yeah, it's a huge problem. NHS, if you Google it, you'll find out NHS keeps on revoking the use of surgical meshes, and then the Royal College of Surgeons comes and says, no, this is the best way that we can do. Even if there are recurrences, we have to go for surgery again. So there's a back and forth going, but the problem still exists. Now, going to the solution that I'm submitting is a cellular materials. So cellular materials are found in nature. We have been inspired by nature to look for cellular materials, and quite good examples are honeycombs and the nest of wasps. So what is cellular materials? They are open structures. You just do not create a continuous material, but instead you build like small cells. On the right over here is a good example of octet truss lattice, which is made of steel material. It's quite lightweight. You can see the relative density is quite less. There are a lot of air spaces inside. So they're quite lightweight. Second thing is the mechanical properties can be tuned. That means if you give me steel and I have a fixed strength and elastic modulus, now if I design it as different unit cells, honeycombs, hexagonal honeycombs, or maybe triangular cells, or maybe this 3D octet truss, then the unit cells will dictate the properties. So the mechanical properties can be tuned based on the unit cell. Secondly, if you change the relative density, which is nothing but you change the dimension of these cells, you can also get another advantage on the mechanical properties. And clearly visible is you can change the porosity. So these three are good markers for me to begin that, okay, why not we use cellular materials for surgical meshes? Now the methodology that I adopted is I wanted to know when I choose a particular material, suppose I choose polypropylene, what unit cells should I decide and what should be the particular relative densities? To know that, to come up with a very general map, a design map, I had to apply the fracture mechanics, classical fracture mechanics from continuum solids, and apply it to these architected materials. One of the interesting things that I found is these materials, as you can see, they are made up of struts, right? So when you pull those materials on this way, instead of failing or tearing, they can go into buckling, which is elastic buckling. And elastic buckling absorbs a huge amount of energy. That means if I place this mesh, which I have manufactured finally, and I place it inside the body in the lower abdomen, when you sneeze, a sudden impacts, there'll be huge load. Okay, there's a fatigue load, there's a huge impact load. Such impact loads will not cause tearing, because this lattice material can undergo local buckling in the struts, so they can absorb a huge amount of energy. That was a key finding in this study, and I did it with polymeric materials because that's what the surgeons prefer. So low density materials made from polymeric lattices, typically the yield strains are in 2%, 3% range. They will undergo buckling instead of failing. Okay? So I wanted to confirm this in experiments because this is all done in finite element calculations, and I wanted to see how accurate these are in experiments. So yeah, we have to manufacture this lattice specimens, and I cannot do a loading test in huge and strong. I had to make a small arrangement, and I wanted to see it when it happens. So it's an in situ X-ray CT arrangement that I had to build, and the loading is not just uniaxial, it has to be triaxial, because inside your body the loading is from all the directions. So triaxial loading was carried out using this setup, placed inside an X-ray CT, and this is how it looks. Can I? Okay. Can you see the video?
Yes.
Okay, so you can see this, that, oh, sorry. It's just taking a small slice from the city. The struts here have gone into buckling. So this is sudden impact that I provide from all the three directions. And instead of failing, the struts have gone into local buckling. So all the absorbed energy are being absorbed in elastic buckling. So it delays failure, it prevents failure. This was a good point of start, you know. And then I changed the topology. I tried different topology. And one of the topologies I'm showing here is an octet truss topology. And you can see that these struts are, this unit cell is having a dimension of nearly 100 microns, and I have millions of unit cells. And finally, the product looks something like this. So this is a conventional mesh, and this is an architected because I apply an architecture in the design, and cellular, they're open structures, and I'm designing a surgical mesh. So these are more like cushion-like materials. So what are the major advantages? Well, as I told you, the unit cell will decide the anisotropy. So I can control how much anisotropy I want based on the choice of unit cell. Second thing is stiffness and strength. Now, if I use the conventional materials, textile-based surgical meshes, then my strength and stiffness are fixed. But here, I can control it based on the relative density. So it scales with relative density. So I have better control over stiffness and strength. With the same material, changing the unit cell, changing the dimensions, I can control the stiffness. So for suppose example, I need for a very soft tissue, I can go from a hexagon, from an octet to a hexagon and make it very soft. Porosity, you can see it's very direct. You can change the porosity as much as you want. There's definitely an inverse relationship with stiffness and porosity, but that can be fine-tuned, and that's why I had to develop some design maps. So this is a fracture-based design maps. That means these contours are telling me the failure lines, okay? And I want to be in the region of elastic buckling because I want that mesh material to go into buckling whenever impact loads are applied. So suppose somebody tells me, a surgeon tells me that, you know, I want something which is not very tough, it has to be soft, and I choose a number over here, okay? Suppose 0.009 is my failure line. I will not go here, I'll go something here in this region because I know this will absorb huge amount of energy during impact loads. And then based on the porosity requirement, I can also change the relative density. And this T bar is nothing but a structural number, which I have collapsed, a non-dimensional structural number, which I have given over here. So beta is the loading biaxiality. I need to have some idea about how the biaxial loading in the intestine will be. I need to know, you know, what will be the different crack sizes inside that. And then I can decide on this parameter T bar, the normalized, and the porosity, and I can, okay, choose this or this, any point, and design the mesh and give it to the patient. So this are design maps which I've developed, and this can be generated for different topologies, for different yield strains, but they're quite generalized. I mean, you can use it. So when you give it to a manufacturer, you can give this design map, they will know the requirement, they will choose the parameters and just print it. So currently I'm writing a research article based on this because this is not part of my PhD. I mean, it's an extended work which I did. So it's taking up a little bit of time. I need to do a few more experiments, and I need to fabricate a few more mesh and do experiments because they would want more experiments and submit the draft. I'm also applying for clinical approval with the Royal College of Surgeons of England with the help of NHS, and Addenbrooks have been quite helpful in this. And finally, you know, patented the design and name it as architected cellular surgical mesh. And on the research frontier, there's something called hierarchical structures, which are becoming popular now. Now, all this was not possible in the last 2 decades because it's just recently that you can print such small features and scale up to big materials, full-scale material. So hierarchical architecture is something which is not yet possible, but theoretically we can study and see, can hierarchical structures help even more? So yeah, I'm in a stage where I've completed the project and I'm writing a research article, and let's see what happens. Thank you.
Thank you very much, Angkur. Any questions? This is different from the previous one. It's from the photonics to electrical, now move to mechanical part. So I just have a question is about this fantastic material. How about the biocompatibility? Oh,
so because we will not change the material, I'll keep the same polypropylene PP material. I'll just print it as an architected material.
I see.
So it remains the same material. That is one of the biggest advantage, because that's what I thought that clinically getting approval will be easier in terms of infections.
Sure, but will that limit the range of the base materials choice?
Yeah, you can always mix it with polymers and then coat it with the polypropylene.
Okay, yeah, I think that's a good approach. Any further questions? If not, let's thank all the speakers again, and thank you very much for the wonderful talk.
Thank you.
And also thank you for all the people participate in this presentations in this special time, and we get it online, which is very unusual. That's the first time we have done this, and hopefully this will enable more people join us and to widespread the fantastic work done by the students. Thank you very much. Okay, so we'll stop here, and we'll put the video of the presentation online. And if you have further questions or interest in pursue this project further in collaboration with the students, please get in touch. Thank you very much. Thank you.